All right, today we are going on a hunt for a ghost. Seriously, we're looking for a particle so sneaky it could pass right through this room, right through you, without leaving a single trace. Yet, it might just hold the key to one of the biggest puzzles in all of science. We are talking about the dark photon, and the hunt for it, it's one of the most incredible stories in physics today.
So to really get why this hunt is so important, you gotta start with this one truly wild fact. Get this. 85% of all the matter in our universe is completely invisible. We have no idea what it is. We call it dark matter. We know it's there because we can see its gravity pulling on stars and entire galaxies, but we can't see it, we can't touch it, it's just missing. It's a cosmic riddle of the highest order.
And that brings us right into our first section, the universe's missing matter. What exactly is all this invisible stuff?
So, what is dark matter? Well, put simply, it's the stuff that doesn't play by the rules we're used to. It doesn't interact with light in any way. It doesn't shine, it doesn't reflect, it doesn't even cast a shadow. The name is perfectly literal. It's matter, and it is completely dark. The only reason we even know it's there is because it has weight, it has mass, and that means it has gravity.
Okay, so that leads to the really big question, right? What is this stuff actually made of? There are a ton of theories, but today we're going to zero in on one really fascinating possibility, a hidden candidate for what dark matter could be.
To kind of wrap our heads around this idea, let's just ask a question. We all know about light, and we know about the particle that carries it, the photon. But what if light has an invisible twin? A secret cousin that operates in the shadows, a particle that holds the secret to all that missing matter in the universe.
And yeah, this slide lays it out perfectly. On the left, you've got our good old photon, the particle of light we all know and love. On the right, its hypothetical cousin, the dark photon. The theory goes that there's this whole separate, dark sector of reality with its own particles and forces. But here's the kicker, the crucial part. Every so often, a dark photon might be able to transform into a regular photon, and back again. Physicists have a name for it, kinetic mixing. And that tiny little crack between worlds, that's our only way of peeking inside.
So if this particle actually exists, how on earth would you ever find it? Well, this leads us to one of the most clever, almost sci-fi experiments I've ever heard of. I'm talking about literally shining light through solid walls.
This process is just brilliant. Okay, so follow along. Step 1. You fire a really powerful laser into a super strong magnetic field. The theory says that this is the perfect environment to convince a few of those regular photons to switch sides, to turn into dark photons. Then comes the wall, a big, thick concrete wall that stops every single bit of the normal laser light. Gold. But the dark photons, being ghosts, they should sail right on through. On the other side, another magnetic field is waiting, ready to reverse the trick, to turn any dark photons that made it through back into normal detectable light. And the final step is just waiting, with an incredibly sensitive camera looking for a single photon to just appear out of thin air.
So after all that incredible work, what's the payoff? In a basic setup, how often would you actually expect to see one of these ghost photons pop into existence? The math says you detect one, a single photon, about once every 700,000 years. Yeah, that is the insane scale of the challenge we're talking about here.
Obviously, nobody has almost 1,000,000 years to sit around waiting for one data point, so scientists had to get even cleverer. Experiments like ALPS 2 in Germany use this brilliant trick called an optical cavity. Just think of it like a hall of mirrors for light. They bounce the laser back and forth thousands and thousands of times, which amps up its effective power by more than 10,000 times. This gives the photons way more chances to make that jump to the dark side, turning an impossible wait into something you can actually do.
But that's just one way to hunt. Instead of trying to make dark photons from scratch, what if we just listened for the ones that are supposedly all around us already? And that brings us to section 4, where we learn how to tune a cosmic radio into the dark.
This is a completely different approach. The idea here is that the dark matter holding our galaxy together is actually made of these dark photons, and they're constantly streaming through the Earth, through this room, through you, right now. So some experiments are designed to act, as this source perfectly puts it, like effective telescopes for observing galactic dark photons. Only they're not telescopes with mirrors and lenses, they're telescopes that listen. So, how does this cosmic radio work? Well, it all starts with something called a resonant cavity. It's basically a very precisely engineered hollow metal box. And just like a tuning fork or a guitar string, this box is built to resonate, or ring, at one very specific frequency. Now here's the cool part. In physics, a particle's mass is tied directly to a frequency. So if a dark photon with just the right mass happens to fly through the box, it can convert into a normal photon whose frequency perfectly matches the box's. That makes the whole cavity ring with a tiny little burst of energy. And inside, a super-sensitive antenna is just listening for that one single specific note. And here is what one of those cavities actually looks like. You can see it's not just some simple box, right? This is a piece of high-precision engineering, designed to be the perfect trap, the perfect amplifier for one very specific, very faint signal. This is the heart of the dark matter radio.
But there's always a catch, isn't there? The problem is, we have no idea what the dark photon's mass is, which means we have no idea what frequency to tune our cosmic radio to. So scientists have to do it the long, slow, painful way. They tune the cavity to one frequency, they listen for a while, nothing. Then they carefully, painstakingly retune it to the next frequency and listen again. They are slowly, methodically scanning through millions of possible channels on the cosmic radio dial, hoping to land on the right one.
So all this brings us to our final section, and the big question. Where does the hunt stand today? Well, the search continues, and let me tell you, it is a massive, global undertaking.
And when I say massive, I mean it. This isn't just one lab in a basement somewhere. You've got AMDX in the United States, ALPS-2 in Germany, CAST over at CERN, CAP in Korea. This is a truly global ghost hunt. Thousands of scientists are all building these incredibly sensitive machines to check every possible corner where this thing could be hiding.
So, with all that effort, all these brilliant minds, all this incredible technology, what have we found? Well, as one recent paper put it pretty bluntly, they found no significant evidence. And so far, that's the story across the board. The ghost is still in the machine.
Now, it's really easy to hear that and think, well, that's a failure. They found nothing. But in this kind of science, when you are searching at the absolute edge of what's known, finding nothing is actually incredibly important. It is not a failure. It is progress. Let me explain why. Every single time one of these experiments scans a range of possible masses and comes up empty, they get to do something really powerful. They establish what's called an exclusion limit. It lets them take out their map of possibilities and draw a big line through a whole section and say, with confidence, okay, it's not hiding here. With every new experiment, with every null result, that map of potential hiding places gets smaller and smaller. Piece by piece, we are cornering the ghost.
So no, we haven't found it yet. The universe is holding its secrets very close, but every negative result, every new exclusion limit is another step forward. With every scan, the shadows get a little bit smaller, and the places left to look get more and more interesting. Which of course leaves us with that final, tantalizing question. What are we going to find when we finally turn over the right stone? Will it be the dark photon we've been looking for? Or could it be something even weirder? The hunt is on,